Okay, so in this video, we are going to see an example for application of D'Alembert's principle. The example is of dynamics of wheel jack. A wheel jack is an articulated machine which is designed to lift up heavy burdens as shown in the figure. It is composed of two rigid bases, one resting on the ground and other sustaining the burden with weight E. They form an articulated longe with side L, which may be deformed by means of a threaded stem with a step size h. The axis of the jack changes by a length h for each revolution of the crank, which is driven by a force F applied on the crank of arm length A. So let's write down what's given in the question. Length of leg is equal to L and step size is h. We can see that length L remains constant during the change of height of wheel jack, which provides us with following constraint equation. OA square plus OB square equals L square, where OA and OB are defined as the points at the end of each legs as shown in the figure. Let me also mark up the points in the figure itself, just for the reference. Now, due to the rotation of the threaded stem, we can conclude that one complete rotation will result in 2 pi radians of angular displacement, and this will change the length of dB by step size h. By observing the figure, we can say that there is only 1 degree of freedom for this system, which means that if I log angle theta at some particular angle, then there is no movement associated with the jack. The system just can't move. Now let's just consider the virtual displacement of length dB that is caused due to the virtual displacement of angle alpha, which is associated with the rotation of the threaded stem. For example, when we are lowering the system, the change del x, which is small change in length dB, is equal to h times del alpha over 2 pi. That means if for rotation of 2 pi radians, we get change in length h, then for del alpha rotation, we get the change in length del x given by this equation. Thus, we can write del x equal to del dB, which equals to 2 times del OD, which is equal to 2 del OB. This equation is just from the geometry of the device. Thus, in order to satisfy the constraint equation, which is given by the equation 1, the length OA will then be decreased by relation OB squared is equal to L squared minus OA squared. Which can also be written as OA squared equals L squared minus OB squared. This is simply Pythagoras' theorem. If we do some simple trigonometry, we can easily see that tan theta is equal to OA over OB, which implies OA equals OB tan theta. The change in length away will then be given by the following equation, where we can see that the sign appears because the length OA decreases as we increase the length OB while lowering the system. Thus, the variation in altitude of load P, as we can see in the figure, will be given by the following equation. Del Z equal del AC, which equals 2 del OA, which then equals to H del alpha tan theta over 2 pi. Now, let's just find the forces acting on the system. The load P acting at point A, which produces amount of work given by del WP equals minus P del Z, which equals minus P times H del alpha over 2 pi times tan theta. The second force which is acting on the system is the reaction force from the ground. This force basically counters the moment produced by the force F, which is acting at the end of the crank. This can be shown in the following figure, where the cross represents the force going into the screen and dot represents the force coming out of the screen. However, since there is no displacement of point C, we can conclude that the work done by the ground forces equals to 0. The third force acting on a system is the force at the end of the crank itself, which is given by F. This force generates torque and angular displacement alpha, so that the work by this force is equal to the torque times angular displacement, which gives minus Fa times del alpha. Therefore, we can conclude that the total virtual work done by all the forces is the sum of their individual work done, which can then be expressed by the following expression. Where QA represent the generalized forces now according to the D elements principle, the overall system is in equilibrium. The generalized forces has to be equal to 0, which then implies that pH over 2 pi tan theta minus Fa equals 0, which implies P over F equals 2 pi A over tan theta H. Thus, we conclude that for lifting higher loads, either crank arm has to be larger or step size H has to be smaller, which implies if pi is greater, then either A has to be greater or H has to be smaller. Okay, so that's it for this video. Thanks for watching and stay tuned for more videos regarding this topic.